I just received the go-ahead from Kevin Murphy. So, thank you, Kevin. Well, good evening, everyone, and welcome to the President's Lecture Series. We're here live, and we're also online, just to let everyone know. Tonight offers us a wonderful opportunity to focus on the positive strides humanity is making across many different disciplines that shape our world and enhance our lives. I would like to begin by thanking Cindy Powers, Director of Continuing Education and Lifelong Learning, for organizing this evening's Nobel Prize lecture. As all of you know, Cindy does an extraordinary job, and we really appreciate it. And your fan club is here. It's wonderful. I would also like to take the opportunity to introduce Dr. Richard Thompson here this evening. He is the new Dean of the College of Science, Technology, Engineering, Mathematics, and Nursing. He joined us in January. He has some big shoes to fill after Dr. Bob Warburton, who's sitting right up front here. So great opportunity for all of you to meet Rick this evening. Rick is going to give us an overview of this evening's event. He's going to introduce all of our distinguished lecturers, and you will truly be impressed with the expertise that our respective faculty will be sharing with all of you. And then, of course, at the end, we have a dessert reception. We look forward to seeing all of you in the atrium for that. And I'll just mention, so Dr. Thompson is going to introduce everyone in the beginning, and we're going to ask you to please hold your questions till the end so that we can do kind of a round robin with all of our speakers. So thank you again for joining us, and enjoy this evening. Thank you.
Well, thank you all for being here. The first presenting on the Nobel Prize in Physics, which was awarded to John Clark, Michel H. Devoret, and John M. Martinez for, quote, the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit, end quote. We have Dr. Seidel Murphy. Dr. Murphy is an associate professor of physics and chair of the Department of Natural and Physical Sciences. She received her BS from Monmouth College, her MS and PhD from Montana State University, where she completed research in optics. Dr. Murphy is a founder of the Seeding Your Future initiative, a K-12 STEAM outreach program with the goal of helping engage and encourage the participants' involvement in STEAM through hands-on activities. Speaking on the Nobel Prize in Chemistry, awarded to Susumu Kitagawa, Richard Robson, and Omar M. Yagi, quote, for the development of metal organic frameworks, end quote, will be Dr. Joseph Locant. Dr. Locant, a West Virginia native, joined the Shepherd University community this past fall as a lecturer in chemistry. I am very happy to note that he will be continuing in the coming fall as a tenure-track assistant professor of chemistry. He completed his Bachelor of Science in Biochemistry at West Virginia University in 2020 and earned his PhD in chemistry at the Ohio State University. I have to say that again, the Ohio State University. I didn't have enough stress on the "the." And he did that in August under the supervision of Dr. David Najib. He is an organic chemist with a particular interest in the field of radical-mediated, site-selective carbon-hydrogen functionalization reactions. Next, we have Dr. Bob Warburton, presenting on the prize in Physiology or Medicine, awarded to Mary E. Brunko, Fred Ramsdell, and Shimon Sakaguchi, quote, for their discoveries concerning peripheral immune tolerance, end quote. Dr. Bob Warburton graduated from the University of Essex at Colchester in England with a degree in biological chemistry before coming to the United States to complete his graduate work. He earned a master's in chemistry and a PhD in biochemistry from Duquesne University in Pittsburgh, Pennsylvania. He was an NIH postdoctoral fellow at the University of North Carolina at Chapel Hill, where he carried out research in molecular immunology. He came to Shepherd in 1993 and is currently professor of biochemistry. His research interests are in the structure and function relationships in proteins. Dr. James Pate will be speaking on the prize in literature awarded to Laszlo Krasnohorkai, quote, for his compelling and visionary ode that, in the midst of apocalyptic terror, reaffirms the power of art, end quote. Dr. Pate is an associate professor of English in the Department of English, History, and Modern Languages, where he teaches creative writing, literature, composition, and philosophy. He has an MFA from the Writers' Workshop at the University of Iowa, a PhD in English with a creative writing dissertation from the University of Illinois at Chicago. His books include the poetry collection Mineral Planet and the essay collection Flowers Among the Carrion, Essays on the Gothic in Contemporary Poetry. Next we have Dr. Samuel Green presenting on the Nobel Peace Prize awarded to Maria Corina Machado, quote, for her tireless work promoting democratic rights for the people of Venezuela and for her struggle to achieve a just and peaceful transition from dictatorship to democracy, end quote. Dr. Green is Director of Study Abroad and Associate Professor of Political Science at Shepherd University. He holds a doctorate in politics from Catholic University of America and a master's degree in internal relations from the University of Cambridge. Dr. Green's academic research examines insurgency and counterinsurgency, democratization, and internal conflict with an emphasis on Latin America and the Middle East. His monograph, Pathological Counterinsurgency, A Critique of U.S. Counterinsurgency Strategy, was published by Lexington Books. He has published numerous academic articles in venues including Democratization, Third World Quarterly, Defense Studies, and Comparative Strategy. Finally, the Sveriges Riksbank Prize in Economic Sciences, awarded to Joel Mokier, quote, for having identified the prerequisites for sustained growth through technological progress, end quote, and to Philippe Ajon and Peter Howitt, quote, for the theory of sustained growth through creative destruction, end quote, will be presented by Dr. Amanda Manzik. Dr. Manzik graduated from Shepherd University in 2008. She attended West Virginia University and received her PhD in economics with a concentration in development economics. Subsequently, she took a position as a lecturer of economics at Penn State University before returning to Shepherd University in 2018. She is currently an associate professor and teaches introductory economics, macroeconomics, statistics, development economics, international trade, and econometrics. Okay, let's welcome our first speaker to the stage, Dr. Seidel Murphy.
I can use it. It doesn't matter. You're like two-fisting this here. Okay, so the Nobel Prize in Physics is for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. I decided to organize this talk a little bit differently because my guess is you have no idea what those words are. So we're going to start by just basically a little bit of introductory physics. Okay, I'm taking it bit by bit. We're going to start, what is energy quantization, right? In quantum mechanical particles, let's try again. In quantum mechanical particles, they can take on particular energies and not anything in between. We say they're quantized because they are only specific values. Energies in between are not allowed. You can think about this as a stair step where you're allowed to have an energy on the step part of the stairs, but not anywhere in between the stair parts. Okay, so now I'm going to give you an example of this that you probably haven't thought about in your everyday life. So 2 questions. First question, if I take a normal light bulb, old-fashioned incandescent glowing wire type light bulb, and put it through a prism, what do I see? A rainbow. You see a full rainbow from the blue to the red, nothing in between that makes it look weird or odd or anything like that. Okay, next question. If I have a neon light, a true neon light, what color is it? It's a gas. It's red. It's red. Okay, so neon lights are like Xerox machines. The first one that was made was neon, so all of them are now called neon. But they're not all neon, right? If I look at the spectrum of the neon light, I put it through a prism, looks like I did my incandescent bulb, I see these series of lines. And you can see that a lot of them are concentrated here in the red, which is why my neon light looks red. But now why do I have these lines? It's because the energies of the electrons in the neon atom are quantized. And now I'm going to show you the big scary picture, right? This is the energy diagrams for neon. I warned you it was scary, right? But what we see is we can have energies up here in the 3D orbital, and if we have an electron that falls from 3D to 3p, it emits a red photon of 750 nanometers, forming one of those lines we saw in the spectrum. And if I start at 3p and I drop down to 3s, I get a whole slew of other red ones. But notice I can't get anything other than the numbers on the chart. The energy levels are quantized. Okay? Okay, the next bit was quantum tunneling, right? So we're going to start by thinking about what happens when we throw a ball. If I throw a ball, I can predict where that ball is going to be at any place and time during its path. Okay? Now contrast that with an electron, where I can tell you where it's likely to be, but I can't give you a definitive answer. Quantum mechanics works on probabilities. Okay? So now if we also think about throwing a ball at a wall, in the classical world, the ball rebounds, and it looks like whoever drew this picture is aiming for the kid's head. Not my picture, just saying, right? In the classical world, that's what happens. Everybody's had this happen once or twice? Yeah. In the quantum mechanical world, there is a probability that the ball will pass through the wall. That is quantum tunneling. Okay, so again, I'm going to give you a slightly less picturesque version of this, right? So, and a definition. In quantum tunneling is a phenomenon where particles penetrate energy barriers that they shouldn't be able to because they don't have enough energy to get out of that particular well that they're in, right? So they can pass through it. And this is because there's this non-zero probability in quantum mechanics that the object's on the other side. So again, here is my well. You can see I got energy going up here. It's got, you know, if you have really good spidey fingers, you might be able to climb out, but in general, you're stuck at the bottom. Because our electrons or our particles in quantum mechanics are quantized, we are only allowed certain energies. So here they are. Anything in between isn't allowed. And then I can look at where is the particle likely to be. So for each of our energies, there's some likelihood of where the particles are going to be. So if I look at this top one, it's more likely to be here than, say, at the bottom. But look over here on the edge. See that green? That green is the probability that the particle's in the wall. Now imagine, instead of having one well, you had two side by side. So we're just, oop, wrong way, right? I'm just going to stick one right over here, where this tail lands in the other well. Now my particle can start here and move to the other one through quantum tunneling. Okay? Okay, so now you got the basis. Let's go back and look at the Nobel Prize citation, right? The discovery of macroscopic quantum mechanical tunneling. The key word here is macroscopic. Everything we've talked about so far has been a particle, an atom, the electrons. This is something that is big enough that in theory you could hold it in your hand, though you're not going to want to because it's super cooled. Just saying, right? Macroscopic quantum tunneling and energy quantization in a circuit. Okay, the three awardees are John Clark, Michael H. Deveray, and John M. Martinez. And I want to point out a really cool feature about these three awardees, because usually it's the guy who runs the lab that gets all the credit. Turns out John Clark ran the lab. Michel Deveray here was his postdoc, and John Martinez was the graduate student on the project, right? Can you imagine doing work as a graduate student and getting a no? Okay, I'm done. I'm not holding my breath, just saying, right? Okay, so how did they do this? What did they do? And this is a really simplified version of a very complex experiment, okay? What we got is they sent up a superconductor, which is why everything has to be supercooled. And in their superconducting wire, they were able to pass a current, but it went through this little insulating barrier, and then it proceeded on its way. Initially, they set this up so that the voltage that they measured with like a voltmeter across this was 0. And they waited a little time, and sure enough, through quantum tunneling, all of a sudden, the voltage they measured was no longer 0. It's an electric circuit. Again, something you could hold in your hand. Probably are right now. How many of you are holding your phones? Right? The other thing they did is they took and they blasted their circuit with microwave radiation. And what they noticed is changes occurred only at certain frequencies of that microwave radiation, indicating that the current that they were using was quantized, because if it reacted to all frequencies, it wouldn't show those distinctive energy levels, right? I'm almost done. I got one slide left. Okay, so what's the application? The application of this is really to quantum computing, quantum computers, quantum electronics, quantum optics. And I wanted to put a picture on this. Did you guys know that a quantum computer looks like a chandelier? Just saying. And that is the Nobel Prize in Physics for this year. Go to the next slide, Joey.
All right, hello everyone. I'm excited to talk to you guys today about the development of metal organic frameworks for the Nobel Prize in Chemistry for this year, for last year, I guess, rather. So we'll start off by here in the middle, we're going to introduce our 2025 Nobel laureates. So here in the middle, the original pioneer of this field was Richard Robson. You can get a little bit of a foreshadowing event of what we're going to talk about today with this supermolecular huge metal organic framework that he has built in his hands there. And then we'll have significant contributions from Susumu Kitagawa, the Kyoto University in Japan. He really helped pioneer the field from a level of a lot of people didn't believe in the applications, the potential applications of these types of materials. And then Omar Yagi at UC Berkeley, he really pioneered the field from a synthesis standpoint and all of the different modifications to these molecules that can have a lot of broad application. All right, so we're going to get into what metal organic frameworks are, and those you'll see these abbreviated as MOFs, as short. So the design here is that we have metal ions that are linked together by organic molecules to create extensive 3D networks, and in doing so, we create these large cavities. All right, so the backstory on him, Robson, that is, creating these molecules to begin with, was actually one from a teaching environment. When he was at the University of Melbourne in Australia, he was teaching general chemistry, I suppose, to his undergraduate students. And back then, they were using ball and stick models. And he actually had them made from just wood and pegs from the shop there at the university. And so building these molecules with his hands and teaching to students about the geometry of these molecules is the inspiration that came for this, this science. So the shape that he was really interested in actually comes from diamond here over to the left. So diamond is this framework of interconnected carbon atoms, right? So there are these tetrahedral four-membered arrangement of these atoms. And he thought about this design. Well, he said, what if we use a metal ion, such as copper, and then we have organic molecule that can link to these copper ions. So he used at first these 4 cyano biphenyls, and so these nitrile groups at the end here were what tethered to the copper ion, and then the tetrahedral geometry around each of these created these very large cavities in which molecules could pass through, and then depending on a little bit of foreshadowing here to the future works, depending on the nature of the compound, could be trapped inside of this framework and then released later on. So that can kind of foreshadow a lot of the application here. So moving on, after Robson in the late 80s kind of introduced this idea, Susumu Kitagawa also contributed to this by adding these stable rigid structures using nickel, cobalt, or zinc rather than copper, and 4,4-bipyridine. And in doing so, he had these channels created. It almost looks like a sort of framework of railroads, and then these channels provided cavities in which gases could be trapped, right? So they were pretty efficient at trapping gases. However, there was a lot of pushback from the community on this and the application of these compounds, because they turned out to not be very stable, right? And so at the time, we also had, of course, zeolites, which are silicon dioxide frameworks that were very good at trapping gases as well. All right, so in order to continue to receive funding and push this field forward, he had to really think outside the box on developing flexible MOFs, right, that are able to adapt and really increase the applicability to different gases and compounds and things of that nature. So Kitagawa was really credited with pushing the field away from a lot of doubt on the early side. And then Yagi in the United States continued this work. In 1995, he actually coined the term metal-organic framework. And then he continued, and at that time, actually in 1995, he was working with 2-dimensional structures. And then he advanced his work into metal-organic frameworks that are 3-dimensional in shape. And these MOFs that he created turned out to have a lot of application in the sequestering of water, carbon dioxide, and things of that nature. So he introduced in 1999 MOF 5, which was very unique because we had these carboxylate linkers. So there's these aryl rings that are linked by carboxylates, and they bind to zinc metals in order to create this cubic framework with a lot of cavities in between, in order to create a lot of space for molecules to be trapped and then sequestered and then eventually released. And he continued to develop this. I remember Yagi was really instrumental in pushing the synthesis side of this work. So he developed a lot of different linkers. So you can see the size of the organic molecule between the metal atoms here creates different cavity sizes for a broad range of molecules to be trapped and then released. So it really expanded on the application of this chemistry. And you can see up here a lot of the different linkers that he included in his work. So some of the notable MOFs, and these are really cool structures to look at. MOF 303 here, he was able to capture a lot of water vapor, so including nitrogens and these rings interwoven into the metal organic framework. He was able to create extensive hydrogen bonding networks to sequester water, even in very dry desert-like conditions. And then we have an array of different compounds that have been created since then. So just a couple more examples of MOFs here. Just incredible applications from being able to, with ZIF8 over here, used to sequester rare earth metals from wastewater, and then CAF20, good at sequestering carbon dioxide and releasing it back into a pure form. Just a lot of different applications for these compounds. And with this, now today, more than 100,000 unique MOFs have been reported. And it's a field that continues to grow, and the impact is very broad and spans many disciplines. So now a lot of this work is being used into scale up for industrial impact, and then a lot on the medicinal side too. So drug delivery, targeted in the body and things of those aspects. And Yagi is very interested in the AI aspect of pushing this chemistry forward, because you can use a lot of different modeling to predict the molecules that are going to be able to bind and be released, and a lot of different impacts will be able to come in the future years as predicted from this chemistry. I really like this graphic. It's kind of a take-home message that they had on the Nobel Prize website. This is kind of resembles a little apartment for molecules to live in. So you have these frameworks created, and you have individualized environments in order for these to exist. And because of that, a lot of specialized compounds can be created, and this field is going to continue to grow in its impact. And that is the Nobel Prize in Chemistry.
Luckily, the remote doesn't have too many buttons. Thank you. So the title of the talk is here, but really it's a case of, I don't believe you. That's really what these people had to fight. I don't believe you. I don't believe the results you do. I don't believe the applications. And I'm just going to basically ridicule you. And that happened for decades. It wasn't just that. So they were persevering. So here's the classic Nobel Prize caricature that is created. So I specifically went out and I looked for the pictures that were used to create the caricatures. Hopefully the animation works. So that's that one, and that one, and that one. And so they shared the prize equally. But I also have another member of the group right here. This is a classic B6 black mouse, and this is one of our major players in the work that was done. So let me go back in time, and the field has been literally littered with Nobel Prize winners as we understood the immune system and how the immune system worked, and how things that worked around for in terms of illnesses and cancers and autoimmune disease and viral infections and all the other bits and pieces. And so we start in 1980. I think we know what the surface of a cell looks like that we can use for immunology. Then we have Tanagawa and his work in terms of how do we have the diversity. The immune system has to protect you against things it has never seen. If you get an illness, it has to be able to protect you against that illness. And so how do you do that? You have to generate molecules that have great diversity so that if you encounter a flu bug today and there's a modification, a mutation, it can then attack the next flu bug and the next flu bug. Rolf Zinkernagel, Pete Doherty effectively looked at how does this work in terms of individual cells. And we talk about T cells and we talk about B cells and all the other bits. And the T cells have really good titles. They're helper cells. There are natural killer cells. There are cells that are associated with finding things, alerting the immune system and saying, okay, we're invaded, there's something wrong with us, we need to fix it. Basic immunology in terms of this is an antigen-presenting cell, and the antigens that are being presented, antigens are basically just fragments of the world around them or in them. In the case of a class 1 molecule, it's basically saying, this is what's happening inside the cell, and everything is fine, don't worry about it, and we do what's called painting. So they put these little fragments on the cell and say, we're fine, everything's cooking, we're doing good, no problem. But if the cell is invaded by a virus, fragments of virus now appear on the cell and say, you know, this shouldn't be here. The T cell, in this case a CD8 positive T cell, if this is a normal U peptide, it ignores you. That's self. It doesn't want to attack self. Everything's good. But if this is a viral peptide, then that is non-self. Kill it. And the whole process is very carefully called programmed cell death, or apoptosis kicks in and the cell dies. Class 2, which is over here, is a different thing. It's telling the world what's around it. So it brings in things from the outside and fragments them and then puts them back onto the surface. We call it painting. And it basically says, these are normal things around me, everything is fine. But if they bring in a virus or some other component into the system that shouldn't be there, it says, you know, I'm living in a very dangerous world and I may be infected. I'm living in a dangerous world. I may be infected. Kill me ready now to protect the rest of the organism. So it's almost like a sacrificial process. So what do these things look like? This is looking down at the top of the antigen-presenting cell. This is a class 1 molecule, and this is the antigenic peptide. They're usually somewhere between 8 and 10 amino acids long. And Peter Parham at Stanford once described this as a hot dog in a bun. There's the hot dog and there's the bun. And I did work on this little port right here in terms of my postdoc work. So this is a more dramatic combination picture. This is the T cell that's scanning and looking for things and trying to see what happens. This is the antigen presenting cell. And you can see it's a very complicated three-dimensional structure that is trying to read and look and see at what's happening. The T cells originate from the thymus, and when you were born, it was about here. And it was there until you were maybe about 5, up through about puberty. And what it did was it literally made bunches and bunches and bunches of T cells. The way that it makes them is by shuffling genes to make differentials. And they think that it could probably make 1 followed by 15 zeros, different combinations. This is how it recognizes all of those different pieces. But some of those combinations will recognize you and try to kill you. Self. So what we have to do is go through a process of ontogeny where we filter out the self-seeking and only look for the non-self-seeking. Sometimes it goes wrong. This is what we call autoimmunity, where the immune system attacks the cell. This comes into things like rapid onset juvenile diabetes, ankylosing spondylitis, and various forms of rheumatoid arthritis come into this process. So what you have is in a T cell system, we shuffle through the process, we make every variation that we can. Over about a 10 to 12 day period, there's a scanning and a filtering, and then if they pass muster, they go out into the world and they stay in your lymphoid tissues. And every now and then they come out and they just scan and they go through it. So it's almost like we're stockpiling our defense mechanism. Big change. We're now in 1942. And we're at Oak Ridge, Tennessee, and as part of the Manhattan Project, and this is where Glenn Seaborg was purifying and enhancing uranium and other compounds, the problem they were dealing with was this stuff that was recognized by a guy by Becquerel called radioactivity, and how that might cause damage. So one of the studies they were doing was, how does radiation affect cells? And one of the things they came up with in 1949 was they had a spontaneous production of a mouse called scurfy. It was a B6 mouse, and something went wrong with it. It spontaneously had a mutation. That mutation led their skin to be scaly. Their fur fell out. Actually, it sounds like me. Scaly and fur falling out. And they had this system generated. You can actually buy scurfy mice, by the way, from Jackson Laboratories. It costs you about $3,200. So now we introduce you to the Nobel Prize winners. Sakaguchi basically went against the tide. The previous Nobel Prize winners I presented you to, we thought we knew everything. We knew self and non-self, but people said, well, sometimes things go wrong. How are they going wrong? And there was a series of experiments that couldn't be reproduced. There was data that didn't make sense. There was literally people saying, this is bogus, this is horrible. Well, Shimon Sakaguchi said, you're challenging me. You're telling me that I can't do something? I'm going to go and try to do it. We're now talking decades of work. And what he did was he went back through a series of previous results. And what he found was if you took a newborn mouse and you removed the thymus, right, this should remove all your ability to make T cells, then effectively they would get sick. The problem was that if you took the newborn and you removed the thymus about 3 days later, you should still have no T cells. But yet what happened was massive amounts of autoimmunity occurred. So we did a series of experiments. Let's take a healthy donor and transfer the stuff, and we'll protect them. But what's happening to the sick mouse? That's the question. Well, it turns out it was male mice, and it was on the X chromosome that they inherited from their mother that there was something wrong. The X chromosome in mice has about 170-some million bases. They narrowed it down to 500,000 bases. It was 20 genes, and they literally examined every gene. And wouldn't you know it, on the 20th gene, they found the one that wasn't working. Turns out there's a human illness that's very similar to scurfy. Happens in male children but they become very sick and they die early. So they literally generated data from pediatricians around the world, desperately looking for the gene, and they found it, this FOXP. Now, what does this thing do? Here's the whole gene system, and there's the difference. AG went to AA. That's the whole difference, one base change, but it generated massive problems for the mice. And Sakaguchi said, you know, maybe there's something going on here. And what he found was that, and we're now looking at 2000 or so, these new forms of T cells that had never been seen before, they were helper T cells. And basically what happens is the T cell comes in and goes totally berserk. That's actually how it's described, berserk. And what they have is, no, it's okay. These regulators say, it's okay, we're fine. You can recover, you can slow down, you can survive. Don't worry about it. When they first produced his paper, no, I think you got it wrong. I don't think the data is wrong. I think something's going on. And this is where the other two folks came in. The other two folks identified the gene and identified the cell tissue pieces, and this is why we need to do this. In the autoimmunity, we can prevent autoimmunity by giving you regulator cells. If you have cancer, cancer cells hide behind regulator cells. We'll remove the regulator cells so the immune system can clear it. And finally, if you have a transplant, this is no longer self, this is somebody else. We'll protect that by, again, putting in these regulator systems. 20 years between different pieces, people saying you're wrong, people saying you've got it wrong, you are wrong. Congratulations, you've just won the Nobel Prize because you were right.
All right, just want to make sure that I have this. You're good, all right? The 2025 winner of the Nobel Prize in Literature was a surprise to many people, including the author himself. Laszlo Krasznahorkai, the 72-year-old Hungarian writer who is a recipient of the 2025 Nobel Prize, is an author whose fiction is known for two central attributes: its feverishly experimental style and its acidly bleak and yet comic sensibility. Unlike many Nobel Literature winners, Krasznahorkai's work doesn't offer a particularly uplifting message. And also, unlike many winners, he's not a realist in the usual sense of the word. However, like two of his main influences, Franz Kafka and Samuel Beckett, Krasznahorkai focuses on individuals who live at the margins of society, far from the centers of power and wealth, and who inhabit a world of absurdity and desperation. Also, like Beckett and Kafka, his stories are less plot-driven and instead propelled by his characters' often manic search for some sort of meaning, a meaning that is perpetually deferred. And yet, for all their pessimism, Krasznahorkai's stories and prose pieces hold an undeniable intensity and power. Susan Sontag once called the writer a master of the apocalypse. And the Nobel Committee, who awarded the prize to Krasznahorkai, said they did so for his compelling and visionary oeuvre that, in the midst of apocalyptic terror, reaffirms the power of art. They further stated Laszlo Krasznahorkai's work can be seen as part of a Central European tradition characterized by the absurd and grotesque. Important features are pessimism and apocalypse, but also humor. And that's the writer there. So who is Laszlo Krasznahorkai? Krasznahorkai was born in 1954 in Gula, Hungary, which is near the Romanian border. He grew up in a middle-class family. His father was a lawyer, and his mother worked in the social welfare ministry. In his early life, it seemed as if Krasznahorkai would follow in his father's footsteps. He studied law for several years in Budapest. Yet, he had long been an avid reader, and at the age of 24, he switched his studies to Hungarian literature and culture. It was around this time when he started to write fiction. Krasznahorkai's first novel came out in 1985, when he was 31 years old. titled Satan Tango, which, when translated into English, means Satan's Tango. It's very close to the name of the village in the book. The novel was a commercial and critical success in Hungary, and Krasznahorkai was immediately seen as an important voice among his generation of Hungarian writers. The novel also included what would become trademarks of his style and sensibility. The story takes place in an unnamed, impoverished Hungarian town over the course of several rainy days. A conman arrives and tries to convince the village that he can save it somehow. Characters scheme and exploit one another and sometimes have prophetic visions. Little happens in terms of plot, but a great deal happens in terms of the characters' interior lives. The book starts with a quotation from Franz Kafka. In that case, I'll miss the thing by waiting for it. In Satan Tango, the characters are waiting for some monumental revelation, some vision of insight that will give their lives meaning and substance. But that revelation is continually placed further and further on the horizon. Like so many of Krasznahorkai's works, it is more about anticipation than epiphany. Through the late 80s and 90s, Krasznahorkai traveled extensively, living a somewhat nomadic existence. He spent time in Berlin, Kyoto, and New York City. He also traveled throughout China and wrote a slightly fictionalized account of his time there called Destruction and Sorrow Beneath the Heavens, which was published in 2004. It was also during this time that Krasznahorkai started his collaborations with the Hungarian filmmaker Béla Tarr. The two of them brought several of Krasznahorkai's works to the big screen, including Krasznahorkai's first novel, Satan Tango. Despite his travels and film collaborations, Krasznahorkai remained a very prolific writer and still remains a prolific writer. He's published 11 novels, 4 novellas, and several short story collections. Many of his novels have been translated into English. That's still from one of Béla Tarr's films of Krasznahorkai. You can see from the still the bleak atmosphere of quite a bit of his work. So what are his major works? 1989, his 1989 novel, The Melancholy of Resistance, is probably his best-known work here in the States. It is about a strange circus whose major attraction is a stuffed whale. It arrives in a small town in Hungary. Soon the townspeople begin to spread rumors among themselves that circus has sinister designs on the town itself. As with many of Krasznahorkai's stories, the imagery in the novel adds greatly to the story's melancholic mood, with the narrative unfolding along a backdrop of rain, fog, and mud. The weather in his stories is continually grim. Again, from the film still, gives you a pretty good picture of what the atmosphere of his novels are like. Another much discussed work is Herman, a novella from 1986. Somewhat confusingly, but in keeping with Krasznahorkai's fragmented writing style, the novella tells the same story, but from 2 different angles. The first angle, called The Game Warden, is about a game warden named Herman, who starts to feel a harrowing anguish due to the number of animals he has hurt or killed. And he believes that not even God can forgive him for his transgressions. In response to this crisis of conscience, Herman begins to hunt humans instead, believing that humans will always be in perpetual warfare against animal life. The second angle to the story, The Death of the Craft, focuses on a hedonistic, nihilistic cult that moves to the town that Herman is terrorizing. The cult begins to be obsessed with Herman, and they begin to relate Herman's type of nihilism to their own particular brand of Epicurean nihilism. In terms of Krasznahorkai's literary influences, two major writers who I've mentioned in the first part of the talk. The first, and probably the major influence, is Franz Kafka. Franz Kafka wrote several short stories and novels in the early 20th century, and his work explores the absurdity of existence, a continual theme in Krasznahorkai's own fiction. And one of Kafka's most famous stories, The Metamorphosis, a character, Grigor Samsa, wakes up one morning to find himself turned into a gigantic insect. No reason is ever given, it simply occurs. Kafka's story follows Samsa's life as an insect, and especially the tensions between Samsa and his family. This sense of mystery and dread in Kafka's work, this sense of living in a universe wildly beyond our comprehension, is a key part of Krasznahorkai's fiction as well. Another influence is Samuel Beckett. Samuel Beckett is probably best known for his mid-20th century play Waiting for Godot, which is about two characters in a barren landscape waiting for the mysterious Godot, who never arrives. Who Godot is and why they are waiting for Godot is never entirely clear to the pair, why the pair wait, but they philosophize about the emptiness of their lives to pass the time. Like Beckett, Krasznahorkai is fascinated by the question of what life looks like at its barest and most vulnerable. And, like Beckett too, he mixes bleakness with comedy. Absurdity, his work suggests, isn't just troubling, but also deeply funny. In closing, I would say that for me, Krasznahorkai is a fascinating writer. His work is difficult, no doubt about it. He tends to write in sentences that go on for pages. In fact, the novella Herman is an entire one-sentence story. It's about 40 to 50 pages, one sentence. So he's a very difficult writer stylistically. And also his bleakness, to say the least, is very bracing as well. But his willingness to not gloss over the strange and sometimes grotesque, and his commitment to his peculiar vision, he really is inspiring. His speech to the Nobel Prize is much like his fiction, huge sentences. Just so he's very consistent in his aesthetics, in his writing, even to the point of making a Nobel Prize speech, which sounds like an avant-garde text, basically. And for those reasons, there really simply is no other writer working today who is quite like Krasznahorkai. He really is unique. Oh, thank you. Uh-oh. Oh. No.
The clicker that does not work. We'll see if that's the battery user. All right. So if you like Dr. Pate's presentation, you might like mine as well. Because this is about a peace prize, but really instead it's more going to be a morality tale about power and about not getting what you want. This was awarded to a Venezuelan political figure for, quote, her tireless work promoting democratic rights for the people of Venezuela and for her struggle to achieve a just and peaceful transition from dictatorship to democracy. But between the awarding of the prize and today, several other events took place in Venezuela which sort of raised questions about all of this citation. So what I'll do is talk about my framing, about the sort of morality play of power, and some of the challenges of awarding a prize to a political figure, and then I'll tell you a little bit specifically about Venezuela. So what's the Nobel Peace Prize all about? It's meant to be awarded to someone who, quote, has done the most or best work for fraternity between nations, abolition or reduction of standing armies, and the holding and promotion of peace congresses. But more or less, the first two tend to define how we think about the prize today. Peace between countries, reduction of violence. So here is the Nobel laureate for 2025, Maria Corina Machado. And I'm essentially going to make an argument that usually when the Nobel Committee awards a prize to someone who is currently doing politics, the prize collides with power. Either the power interests of the person who is doing politics who is awarded the prize, or the power interest of someone else, and often leads to results or outcomes that are very much at odds with the ethos behind the prize. You can call this perhaps the Nobel curse. Many of you recognize this figure, Henry Kissinger, maybe one of the most infamous examples, but I will very briefly talk to you about 4 more recent Nobel laureates, all sitting political figures, all of which who won the Peace Prize, but there are also really serious questions about peace. All right, Abiy Ahmed, Prime Minister of Ethiopia. Right, there is his portrait, and there's civil war in Ethiopia. Within a couple years after the prize, which is awarded for peace between Ethiopia and Eritrea, you have incredibly serious allegations and also a question about whether this peace is real. Juan Manuel Santos, a lot of these pictures are from the Defense Department because they're in the public domain, but this also represents, as he's being awarded the prize, information is coming out about the false positive scandal in Colombia, where the Colombian armed forces, under his command as defense minister, killed civilians and said they were insurgents. All right. I've criticized pretty much every recent American president in print, so don't worry. There's Barack Obama getting the Nobel Peace Prize, and in many ways a repudiation to George Bush, but I don't really think the Obama administration's approach to foreign policy, and particularly its approach to using predator drones, the so-called dronification of American defense strategy, was necessarily what the Nobel Committee had in mind. This is, of course, a question of national interest, but there's also a question about how that fits with someone's status as a Nobel laureate. And of course, the sort of tragedy of Aung San Suu Kyi, who is here with Hillary Clinton. She's awarded a Peace Prize, and then she's at the International Court of Justice defending Myanmar against charges of genocide. So what all these people have in common with our current laureate is they were awarded a prize for peace, but peace was not necessarily the future outcome. And this leads us to Venezuela, part 2, and my Venezuelan morality tale. All right. So the context in Venezuela is very bad. Nicolas Maduro was not just an unpopular leader, but really a morally bankrupt leader. Someone whose security forces engaged in forced disappearances. Someone who wrecked the Venezuelan economy. Why are Venezuelans protesting? Insecurity, injustice, incarceration, censor, violence, corruption. Right. There are very good reasons to not want Nicolas Maduro in charge of Venezuela. Right, but when you look at the 2 pieces, why did the Nobel Committee award a Peace Prize to Barack Obama? It's pretty clearly we wanted to repudiate the Bush era. So President Trump, pictured in this picture, has been very vocal about desiring a Nobel Peace Prize. And the Nobel Committee very much did not want to award a prize to Donald Trump, but it picked someone who is a conservative opposition politician against an odious leftist. But in doing so, really no one got really what they wanted. Right? What President Trump wanted was not someone who he had some affinity with to get the prize. He wanted the prize. And of course, what Machado wanted was to become the leader of Venezuela, which we'll see also doesn't happen. And what the Peace Committee wanted, was a peaceful transition of power. So we have this photo op of 2 people who aren't getting what they want. All right. Here's Delcy Rodriguez, not the Nobel laureate. In fact, the vice president of Nicolas Maduro. So the United States, if you haven't been following Venezuelan politics, conducted a special operations raid, seized Nicolas Maduro and his wife, removed them to the United States, where they're being charged on drug offenses. All right. But the United States did not install the Nobel laureate, the opposition leader. The United States is working with the vice president of Nicolas Maduro. All right. So this is a transition. But is it a transition to democracy? It's difficult to say, but Delcy Rodriguez is certainly not someone who I would consider, as a scholar of Latin America, a Democrat. Was this peaceful? The United States has a long history of removing leaders, some of them very odious, some of them not. But we can look at Manuel Noriega, we can look at Saddam Hussein. None of them, I think, will be on the list for your dinner party. But this is not really a peaceful transition either. So this is sort of my broad theme or lesson that I think this Peace Prize has for us. And that is, it's a very difficult and uncertain thing to award a prize for peace to someone who is still participating in a game of power. And unfortunately, this sort of reinforces a rule common in the study of politics and international relations about the significance of power and the attraction of power. So the sort of second piece of the morality tale is, very often when we exercise in politics, we don't necessarily get the person exercising it what we want. The exercise of power is uncertain, and both in terms of awarding a prize and in terms of removing a leader, the outcome is very uncertain and doesn't necessarily have so much to do with peace. And that is where I will leave you. Gonna work on my peaceful transition.
Well, good evening. My name is Mandy Manzik, and it is my pleasure to introduce the ideas and the contributions of the 2025 Nobel laureates in the field of economics, Joel Mokyr, Philippe Aghion, and Peter Howitt. We live in a really incredible period in human history. If we think about just the technological advancements that we've seen in just very recent years, it's amazing to see how far we've come. But the real anomaly is if we think about thousands of years of human history and how it has only been since the Industrial Revolution in about the mid-1800s when we've seen growth just take off in a way that has compounded as never before in all of history. So the question that these Nobel laureates were looking at from different angles and from different perspectives was what has sustained this growth that, again, that didn't ever occur before in human history, and what can we do to make sure that we can sustain that growth going forward, especially with a lot of the questions that have come up in recent times with new advancements in technologies, and in particular, AI. And one thing that we can point to for sure is it's not because people suddenly became creative in the 1800s, because all throughout human history we've seen amazing innovation in technology, advancements in different civilizations, things that astonish us today and amaze us. However, it never translated into the same kind of compounding growth that we have been seeing since the Industrial Revolution. So that brings us to our first Nobel laureate, Joel Mokyr, who is an economic historian. And he looked at specifically identifying the prerequisites for the sustained growth through technological progress. Okay, so the question is, again, what was it about this time period in the Industrial Revolution that made it right for this growth to start taking off the way that it did? And he divided knowledge into two different types. On the one hand, he referred to prescriptive knowledge, which is knowing how to do something. Okay, so if you come up with a new invention and you create a how-to manual, other people can replicate that and they can make it again. Okay, that will take you to the next level. But again, once you master that, it may not leave you anywhere else to go. We start to experience diminishing returns. Okay. However, if you understand the why something works, which he referred to as propositional knowledge, this is something that could power you to the next level, because not only do you know how to do it, but you also know why something works. And so that lends itself to having applications in other fields and allowing you to continue and to compound that innovation. All right, and so we see this here in this very nice image put out by the Nobel committee with something like the steam engine, which again is very much known for being one of the drivers of the innovation during the Industrial Revolution, how it had these amazing spillovers into other inventions, which would allow, again, the innovation and technology to continue to grow. So it didn't just stop at the steam engine itself, but would lead to innovations in railways, and steamboats, and factories. So that leads us up to today, where we are with artificial intelligence. And again, we can just think of countless ways, and there are so many things that we can't even imagine at this point in terms of applications in other fields if we continue to compound the innovation that takes place. Mokyr looked to see, again, not just this idea of dividing knowledge into these two different areas, but what was it that was really taking place in the Industrial Revolution that allowed for this knowledge feedback to kind of take place, where there's this, interplay between this propositional and this prescriptive knowledge. And he actually looked at a cultural transformation in the framework that, especially in Europe, where things were starting to take off, there was this effort to seek and to share understanding, and also to be able to use it economically. And so we can look at some of the conditions that made the Industrial Revolution the right time. Just prior to the Industrial Revolution, there had been the Enlightenment. Okay, and so you have so many different amazing thinkers in different fields and disciplines that are starting to look at the world and the why things work, and starting to be able to apply them across different fields. However, the thing that was so important here is that this didn't occur in isolation. So you didn't come up with an idea and keep it to yourself, but it was shared. Okay, so via things like the Republic of Letters, there started being connections being made, again, across this European community, where individuals were able to share ideas and piggyback off of ideas and use that to further catapult discoveries and different applications to be made. Okay? And of course, communication was becoming increasingly more accessible in terms of using things like the printing press, being able to spread knowledge and information. So that was also a key component of this time period. And Mokyr, in particular, looked at some of the things that were present in Britain at the time. Not only there was some openness relative to other parts of the world in terms of discourse, but also he underlined the importance of the patent law. Okay, this idea that if you come up with a new idea, you have the opportunity to benefit from that. Okay, so if you come up with an idea, you should reap the reward of what you're doing and the contributions that you're making to society. Okay, so this is going to be a really important component, this idea of being able to benefit from the hard work that you're putting into the innovation that is, again, making the world a better place. Adjoan and Howitt also looked at this idea of sustained growth, but from a slightly different perspective, specifically through the idea of creative destruction. And if you're familiar with the term creative destruction, this was not something that they had invented. This is something that is usually identified with Joseph Schumpeter in the 20th century. But they took some of those ideas and kind of applied it in different ways to how we've had this sustained technological growth. So creative destruction looks at this idea that over time, what we see is that new ideas will replace old ideas, old ways of doing things, okay? And so we'll see industries or, again, certain ways of doing things are being maybe replaced by newer ways of doing things. And this term is kind of twofold, because on the one hand, we see the destructive part of it, and there's can be some fear and anxiety that people will have about what's going to happen to my job. So this is dated back, of course, to the Industrial Revolution itself, where when the power loom came about, there were literally workers who worked in the textiles that, again, were upset because they lost their job to this automatic machine, okay? And so they resorted to physically trying to break the machines. Okay, so clearly there's an antagonism a lot of times to this new technology and what that might do to people's jobs. But at the same time, we can't lose sight of the creative aspect of the creative destruction, okay? And so there's this idea that we have this competition among all the different players, okay? And you have ideas and you're trying to vie for that top spot, okay? And so only one person can get to the top, and when you do, you might knock off somebody else who was already there, okay? And so while that may seem, again, that is the destructive aspect of that, what we've seen historically is that has been good for society. And we can see that right here, the juxtaposition of two different industries, one that replaced another, and I think we don't tend to think about riding in cars, but there was a time in history where that meant another industry was going to go by the wayside. And so I think we would agree that has made things a lot more efficient today. All right, Ajuan and Howitt also looked at this idea of a U-shaped relationship between innovation and competition. And so the idea was here is that competition is going to allow there to be more innovation. And there is an optimal level of competition, and that occurs, again, at the peak of this U. Now, if there's too much competition, you might be in a situation where you have so many different competitors in a market that it's almost cutthroat. You come up with an idea, and somebody instantly steals your idea, and there's no benefit to you for coming up with that idea, okay? So that would be on this end of the spectrum, all right? We can also think about on the other side of the U, where we have a monopoly, and so they own the entire market, and there's another case where there's no incentive to innovate because you already own the market, and so you don't need to do anything to appease the consumers. So that's, again, also not optimal as well. So instead, in the middle, we have this optimal point, and policies that would promote this kind of thing would be allowing people to have some protection of their intellectual property for some time so that they would be able to benefit and be rewarded for their efforts. But at the same time, they shouldn't own that property forever, okay? And so there should be some time limits in terms of how long you can kind of own that. And of course, making sure that there aren't monopolies that are going to be inhibiting competition. The Nobel Prize press release states that in different ways, the laureates show how creative destruction creates conflicts that must be managed in a constructive manner. And so if we think about competition or sports, when you have a race, there's only going to be one winner of that race. But just because somebody comes in second place doesn't mean that they can't also benefit from that. They can make them better, and it doesn't mean that they also can't race again. So there's opportunities for people to come back in, even if they may have lost one time. Okay, one of the biggest takeaways, too, is the importance of having institutional structure or the rules of the game to make sure that everything's going to be fair. And so that was another important aspect that they underlined in their work. And so to end here, we are at a point in time where, again, there's a lot of uncertainty about what the future holds with AI. And of course, there are fears. There's anxiety about what's going to happen to certain jobs. Will things be replaced? But then there's also a lot of unknowns about what new opportunities might be opened up. And is this a pathway of creative destruction? And so this award couldn't have been presented in a more timely point in time. And so we look forward to the optimistic hopes for the future of what this can bring us. So, thank you.
Thank you again to all of our faculty. If you want to give them one more round of applause. I also just want to say thank you to Dr. Hendricks, who started this lecture series, 12 years ago? Something like that? 10 years ago? 10, sorry. Yeah. And it's been such a gift to our community, and I've really enjoyed working on this with you, so thank you. And now I just wanted to open up to questions for our faculty.
I'm blown away. I don't know how many of these. I'm just blown away. This is my favorite lecture. I don't know how many Nobel Prize winning lectures there have been, but I just keep thinking, not for the lecturers, but for our faculty, but how could this be shown again, or could people, I know it's being videotaped. It seems like more people should be able to experience this serendipitous experience, where you're able to understand something that you know very little about because people help you figure it out. So I cannot applaud you more highly. I'm always so proud of Shepherd faculty, as most of you know anyway. That's all. I have no question.
Thanks, Beth. Did I see another question?
Yeah, this may seem a little recent, but where would the effect of that Citrini article on the market fall into AI pathway of creative destruction?
I don't know if I have an answer for that.
Oh,
Yeah, I'm sorry.
I just thought it was a weird response to that article, so.
Any other questions?
How does the Nobel Prize process work? I mean, can I nominate someone to win a prize in chemistry or whatever, or do they just sit around in secret and decide? There must be a very intense process for it.
Yeah, I had that same question too, actually, when Dr. Pate was doing his. Do you know, Saibal?
I know a little bit. Okay, so I'm going to go with year, but it might be several years in advance. Names and studies are put forward to the Nobel Committee to review, and then they sift through all of that, determine who the awardees are, and then the award is made. But the nominations have to come from people in the field. So no, I'm sorry, you cannot put forward somebody in chemistry.
And I can actually add to that. It's interesting in the Peace Prize, which is the one I've looked at. There's sort of a specific list of people who are qualified to make a nomination. What's interesting to me is many of them are very, very narrow. Former Nobel laureates, very small. And then there are university professors, associate professors, or professors emeriti in history, law, and the social sciences. So actually, I could nominate someone for the Nobel Peace Prize, which I was not aware of until I looked that up. So I will have to have a good think. And the great thing is the nominations are confidential for a 50-year time period, at least for the Peace Prize.
Any other questions?
This question is more for Dr. Green than anybody else, but I thought you made an interesting point on kind of the problematic nature of issuing a Peace Prize, not while still living, but while still active. Is there a different proscription that you would suggest for issuing that, you know, whoever it is issued to has to be, for lack of a better word, out of the game for a certain period, or not have the influence that they used to have? Are we acknowledging past successes versus current? Is that a suggestion you might make?
Yes, I think the Nobel Prize for Peace would work much better if awarded to people at the end of their career when they're out of politics, or organizations that aren't participating in politics. If you look at Jimmy Carter, for example, both for his domestic work and for his global work, that's an award that makes sense, and he's not someone who's going to have future malevolence. If you look at award to journalists, for example, who have been persecuted and who are trying to protect freedom of speech, it's unlikely, I mean, I guess theoretically possible, it's unlikely that the journalists, like people like Dmitry Muratov or Maria Ressa, for example, who were laureates in 2021, are going to be seeking political power, the International Red Cross, et cetera. So I think setting that kind of standard, either formally or informally, would be something I would recommend to the committee, although I don't think they're going to call me to ask.
Thank you.
Last question.
Impressive presentations, all of you, so thank you very much. I have one from the economics, and I'm way out of over my skis with this, so be sympathetic. You gave a lot of criteria or a lot of things that came together that caused this massive spike in our GDP growth in the last 150 so years. One of which was the description between a what or how versus why. Why that distinction in the last 150 years or so? And because that's always been the basic root of civilization, asking the question why. Why does that tie into the economic growth so recently been driven by the why aspect?
Do you mean recently, as in since the Industrial Revolution?
Yes, exactly right. Yes.
I think some of the work, especially because Mokyr was an economic historian, he was looking at different civilizations throughout history, which again had incredible technology and inventions. But again, sometimes some of the leaders didn't necessarily incentivize people to continue to, again, benefit off of future inventions and things. And so that's why the patents were so important, is because it kind of carried that opportunity for people to want to continually innovate. And so that's something that he said there are certain conditions that came about during the Industrial Revolution that hadn't been so at the same in the same way, and some of the networking and the communication that was starting to be made internationally made some of that possible in ways that it hadn't been able to before.
Yeah, I can understand that aspect. It's that why versus how. You added that as a component as well. And the other three that you used, I think is fairly obvious. That how versus why, what made it unique after the Industrial Revolution?
I mean, I guess some of the applications come from the why, because that is the how lets you do it again to replicate things, but then the why is the understanding of how you do it and how it can be used in other applications. I think some of the being able to again, piggyback off of the work of others gives you that opportunity to not just replicate, but also go forward on that by using that what if this worked here, and why could we do it in another place and try to do it again? I don't know if that answers.
Okay, thank you all. I hope you'll join us out for dessert out in the atrium, and feel free to ask any additional questions to the faculty.